So we're going to continue. There were some questions in one of the groups. Go on. Is there any questions about the project? Any questions about the project?
Yes, doctor. I have a question.
Go on.
So, as we know, in the low part of the frame of the ship, we have the static force with the pressure. So here we could do as you show in the last homework in 3 assessment 3.8, because you show that we could transform the load to equivalent system with forces and moments.
Yeah, I will explain that today. And what we're going to do is this, okay? We could at the beginning of the session, I said that I was going to apply this process of using energy method, minimum potential energy, to deduce the stiffness matrix of the beam. And then we were going to explain how to convert distribution of forces into equivalent forces and moments. Okay, I'm going to change the order. I'm going to start by explaining this right now. Okay, don't worry. Right now, we are going to explain that. Okay, so let's go to that.
Doctor, a similar problem. I have the after the discrete size, the hull, the ship. This is element I have to load. For example, PX and PJ. It's possible. I can share the
No. Let me explain first.
Okay.
How to convert that, and then we can go on with your questions.
Okay.
Can you see my PowerPoint?
Yes, doctor.
Okay, thanks. Okay, now. Okay, so we're going to follow a similar procedure as we did for the case of the bar, okay? But we're going to change the order, as we said, okay? Instead of explaining the deduction of the stiffness matrix, we're going to go first to the equivalent forces and moment from a distribution of forces. Okay, so remember, applying minimum potential energy to the beam element, okay, is similar to the case of the bar. Okay, so we say this is the potential energy, and this is a combination of U, and this is the, did we use V or W? Let me go back. So did we use V? V, right. There, okay. Now, when we do this, we apply the procedure. Where am I now? Here. Okay, now here, from this U, finally, we get something like this. And this is multiplied by D transpose times D. Okay, now I'm going to leave this right here. Okay, and then I'm going to start with this term. Okay, so let me start by this one, and then in the next session we can do this. Okay, so let's start by this, and we will explain in this way the contribution from the external distributed forces into equivalent forces, which is our concern. Okay, so again, we have three possible situations. First is if we have a body force. In this case, since the body force is related to the mass, so we can think that we can apply a force per unit volume, okay? Force per unit volume. The other we can have is surface force. In that case, we will have force per unit area. And finally, we can have concentrated forces. And then we can have either force or moments on the joints. So we do not need to do much. Okay, so let's start by body forces. So let's convert body forces. Okay, so let's suppose that we have, before we go down, let me, sorry about this. So let's remember that we are working with beams. Okay, so in this case, remember that if this is our beam, this is the x-axis, this is the vertical y-axis, and right now these are the loads. These are the external loads. Okay, so these loads act in the y direction, so they produce bending. Okay, so let's see. What else? For the interpolation, so we said, okay, the displacement I'm sorry, this isn't. Okay, in the local, we use a cubic polynomial interpolation. I say, so we had N1, N2, N3, and N4. Okay, see this is a column. If I transpose it, this is a row. So we multiply this row by the displacement and rotations at the joints. So this is multiplied by D1Y, Phi1Z, D2Y, and Phi2Z. There. Okay, so these are cubic polynomials. And we deduced in class all of these expressions. So this row is completely known. This column are the values at the joints that we're trying to determine. So this is our task right now. Try to determine these values. Okay, now let's proceed. So we're going to consider first body distributed forces. Now the force will be pointing in the y direction. So we call it a big Y, okay? This is body, okay? And this is in the local reference system. So this in general is expressed as force per unit volume. I must insist on this because we need to be careful with the units. Okay, so VE, okay, in this case is specifically for the body. Okay, so we need to multiply this. Since this is force per unit volume, we have to multiply it by dV. So this will be the differential force acting in a certain point. Now, this could displace or can move by this amount. Okay, so this is going to be dVE because this is a differential. And how do we get the full if we integrate in the volume of the element? Okay, so we have something like this. This is the element. The element is defined by two joints. This is our local reference system, like this. So here we have one element like this. This is our differential element. And in here, we have this force per unit volume acting, this Y, acting in this little element. Okay. This V, this is the approximation, this V, we can put it, as we remember, let me, in the previous slide here, or we can put it the other way, okay? Okay, so this is something that we did in the previous class. We can okay. The first element has to be a row. So instead of the other way, we can put it like this. There. So this is a vector, this is a row, and this is exactly as the previous expression, this one. Why? Because V is a single element, it's on a scalar. So the transpose of a scalar is the same. Okay, there. So this is a vector, 4 by 1. So this is a vector. This is a 4 by 1. And this is a row. This is a 1 by 4. And the product will give you a scalar. Okay, now we replace this into here. Now let's go to the force per unit volume, okay? Now, Y, okay, usually does not depend on Y or Z. So if we take this value, will be the same on the section, okay? But we can expect this force to change in the X direction, okay? But it might change in X direction. So when we integrate in the volume, okay, there will be no dependence on Y or Z. So the integration of this will give us an area. So VE of the body will be the integral in X from 0 to L. Then we will have this part here. I will take that in a minute outside because they don't depend on X. This is N. This depends on X, okay? And then we have the rest. The rest will be the integration on a section. Because we're saying that none of this, I'm sorry. I'm missing a term here. I'm missing a term here. It's easy to erase. Here I have Y, the body force, and we expect and we assume that in the section there is no variation, only in the X direction is going to be variation. And then we integrate in the section. Okay? So we assume that this term in the section, okay, if this is the section, there will be the same in this section. But in the X direction, you could have variation of this. Now this will give us, the integration of this will give us the area here that we could have some elements which change the section, the area, sectional area along the X position. But in general, we consider that the section, the section is uniform in the element, okay? So this A, in general, will provide a constant for the integration, okay? So if we consider constant sectional area in an element, okay, let me go back. So this A, this D will be outside, okay? Because they don't change in X. So we could write this as VE of the body will be, we're gonna have the D transpose. So these are the joint displacements and rotations of an element. Then we have an area because this doesn't change. And then we have to integrate in the element. We have to integrate this times Y of the body, which we assume that only depend on X. Or let me put it like this. Let me put this inside here. So, and I will explain that in a minute. There, and then we're missing the N. Remember, this is a group of 4 cubic polynomials, and that's it. Now, this product here, that's what I left it inside. Okay, this is something that we know or we have used before. Okay, so this is going to be, for example, a force per unit length. So this is going to be force per unit length. Okay, remember, this is force per unit volume. If you multiply this by area, the result is going to be force per unit length. Okay, so as an example, so this is the general expression. Okay, once you know this, we know this, you can integrate. Okay, as an example, let's consider weight as a body force. We say we have an element here. This is X and this is Y. Okay, so we have one single element, and this element has a weight. This is weight per unit length. See, this is weight per unit length. So this weight per unit length is going to take this place. But in this case, since we are considering that the sectional area is constant, we can take this value as a constant also. So in this case, W is going to be equal to, this is weight per unit volume times A. So that's going to be equal to this times A. So this is going to be replaced in here. And if A is constant, W is also a constant. Okay, usually we consider that the material of the beam element is uniform. If I have two materials, okay, for example, if you had in one case that you have, for example, steel from here to here, and then we change material, what you can do is we can take one element here and another element here. So you can include the difference in properties. But in each element, usually the material is the same, is uniform. So the material is the same, so gamma is the same, and we assume that the area is constant, the product will be a constant, and that's this one. So let's remember these polynomials, and we can proceed to integrate. And that's the result that we mentioned in the formulation of this project. You will see that in a minute. Okay, so we have that VE as a body, for the body, is equal to, this is a, we don't know, that these are the values that we try to determine. Then we have to integrate from 0 to L. And we know that W, we put it outside because it's constant, and we have to integrate. And now I'm going to remember these polynomials, okay? These polynomials are 4 polynomials, and we have to integrate in X. I'm going to skip the hat because this integration is in the local reference system, okay? So each one of these 4 elements is divided by 1 over length cubed. And in the class notes, we deduce that this is 2x cubed minus 3x squared L. I'm sorry. This is there plus L cubed. The second one is x cubed L minus 2x squared L squared plus x L cubed. The third is minus 2 x cubed plus 3x squared L. And the last one is x cubed L minus x squared L squared. Okay, so Mr. Zamora, you integrate the last one. Ms. Pincay, you integrate the third one. Mr. Jimenez, you integrate the second one. and Mr. Carrillo, you integrate the first term. So you do that, please, and give me the results. Okay, so I'm going to put that this is equal to that, and probably I'm going to get a W out here, and I need to the results. So Zamora, integrate this one, Pincay this one, Jimenez the second, and Carrillo the first one. You integrate that, please, and evaluate from 0 to L. Please do that. Everybody should do it, but I'm going to ask these people, specifically these people, to give me these results. Don't wait for me, please. This is a cubic interpolation. You should be able to integrate very quickly. With no errors, of course. Mr. Zamora, are you there?
Yes, doctor, but I think I'm doing the
integration. Come on, it's easy. So we have something like this. We're taking the positive value, right? So we are doing something like this. This is our W. We have join 1 here, join 2 here. So we're planning to do this, and we're going to convert that into, we don't have yellow. Come on, we should have yellow. Okay, I'm going to use blue for the Ecuadorian national team there. So here, I'm going to put these values. So, Ms. Pincay, you have your result already, Ms. Pincay?
Yes, it's
Okay.
L to the 4th over 2.
Yeah, but L to the 4th. But this is L cubed. So it's going to be L.
I didn't multiply. So.
Okay, so it's going to be L over 2, right? Okay, good. Thank you.
Doctor, similar first. Carrillo.
Okay, so this is L over 2 also?
Yes.
Thank you. We're waiting for these two people, Jimenez and Zamora, this one here.
Yes, Dr. Jimenez, L to the square over 12.
Positive or negative?
Positive.
Okay, and Mr. Zamora?
I have like an expression. I don't know if it's okay because I have L cubed over 4 minus.
Now, if you have, you see here, you have L to the 4th. If you integrate, you got L to the cubed, and you L to the 5th. If you divide it by L cubed, the result is going to be L squared.
Okay.
Minus 1 over 12 multiplied by L squared.
Yeah. Do you recognize this? These are the results that I gave you. So what we're saying is that if we had one case in which this is uniform, remember this is force per unit volume. Now, if you multiply by the area, you get force or weight per unit length. So this you convert into the total forces. These are the forces, and you convert that into half here and half here. So this is WL over 2, WL over 2. Since this is a total weight divided by 2, makes sense. What else? This is a moment, okay? And this is positive. Remember, this is the relative, the system of reference. So we are saying that we apply this moment. This is WL squared over 12. And this one here is, I'm missing the negative here. This is WL squared over 12. So it makes sense, right? So we, instead of having this distribution of forces, we're going to have two forces and two moments right now. So in here, in between, there's nothing. Mr. Zamora, you were asking me something about transformation. This is the way we transform.
Okay, doctor.
Now, these are forces per unit volume. In a second, we are going to talk about forces per unit surface. Okay, and it's going to be similar. So the integration will be very, very similar to this one. We have to be careful with the units, but that's all. Okay. But yeah, now in the case of the, I can warn you, in the case of the hydrostatic force, there is going to be linear variation with the vertical direction. We have to be careful with the vertical direction. Okay. And the problem is that when you have an aligned, or I'm sorry, we have an inclined element, we have to be careful expressing the vertical variation, but that's all. Okay. Questions so far, people? But that's the procedure. Okay, let me go back to remind about this procedure. Okay, so this is the general expression. So this is the potential energy that an external distribution of forces may have. It's the force, it may move in a certain direction. So if it moves in the positive direction, it gains potential energy. That's the idea. So what we do is we replace this expression for the assumption. Remember, this is an assumption. This is not exact. It's an assumption. And we multiply by the force. And the force, we express it as the product of force per unit volume times the volume. Because in general, it can change. This is something that we obtain, chapter 2. So this vector here, it's a vector that we deduced completely. And what we can have is some specific conditions. That's very common. Each one of these elements could be considered as a constant section beam, right? And also in the section, you could have no variation of this force per unit volume, which is something which is very common too. Okay, if you have, for example, in one element, in a section, you can change force per unit volume. Probably what you can do is you can represent that in a more complex way, in more precise way, but you need to put more effort in that, probably to use solid elements or something like that. But in this case, it's quite common to do these assumptions. So this is area, you multiply that by YB, and then you got force per unit volume, for unit length. That's force per unit length caused, for example, by an attraction. And that's typical of volume forces. So in this specific case, when W is constant, these are the results. Instead of this, we have this. Instead of this distribution, we have this concentrated. This is continuous, this is discrete. And we can proceed to solve it. Okay, let's take a second break here. And when we return, we're going to comment on the next type of loading, which is surface forces. Okay, if there's any other question, no, we could try to stop for a break. So I can find where to stop here. Okay, so 5-minute break, people.